Part B of Chapter 8, we're going to focus on the strengths of different acids and bases, and then we're going to finish off with talking about buffer solutions. So strong and weak acids. In a hydrochloric acid solution, the strong acid HCl dissociates 100%. So if we look at this example here showing the HCl, and if we look at the picture, all the green balls are representing the chloride ion, Cl-, after it lost all of its H's, H+. And where do those protons go? After the hydrogen loses the proton, it's going to go on the water, making the hydronium ion. So notice there is no HCl molecules floating around. That's because 100% of them dissociated into ions. A strong acid means that it's a strong electrolyte. A solution of a weak acid of, do you remember the name of this molecule? Remember, I wanted you to memorize that. That's acetic acid. A solution of weak acid of acetic acid contains mostly molecules and a few ions. So here, looking at acetic acid, this particular molecule here, if you don't see a plus sign or a negative sign by it, then it's the molecule acetic acid. Over here, there's a molecule that has a negative sign, so that's the acetate ion. And here's our hydronium. But if you look, most of them are still just the acetic acid molecule. That is a weak acid. Weak acids mean it's a weak electrolyte. So comparing some of the strengths of your how strong some of your acids are, you have a table similar to this in your book. And if you have any homework problems that are talking about the strength of an acid, you'll have to refer to this table. I, on the other hand, am going to let you know whether you're dealing with a strong acid or a strong base, with the exception of one. I want you to memorize that hydrochloric acid is a strong acid. Okay. So acid strength, here's comparing three different acids. We're comparing, do you remember the name of this one? Hydrochloric acid. This is hydrofluoric acid, and do you remember the name of this one? This is acetic acid, written slightly different. So you need to be able to recognize acetic acid written all the different ways. I told you that hydrochloric acid was a strong acid. That means it's going to 100% dissociate. So if I have a 0.1 molar solution, so it's not very concentrated, but if my hydrogen ion is 0.1 molar solution, or the acid is 0.1 molar solution, let me see, I did not say that well. I am going to cut this one out. Okay, let's try this again. The hydrogen ion concentration is here, so the pH is this. Okay. So. This table here is comparing some acid strengths. So let's look at the acids we're going to focus on. Hydrochloric acid, hydrofluoric acid, and here's acetic acid. The percent that they ionize. Well, hydrochloric acid is a strong electrolyte, so it ionizes or dissociates 100%. Hydrofluoric acid is weak, and it dissociates 7.7%. And acetic acid is going to dissociate 1.32%. So 1.3% of these molecules dissociate into a hydrogen ion and the acetate ion. The concentration of the hydrogen ion in a 0.1 molar solution of each of these acids, so here's the concentration of hydronium, and if you use the formula you can calculate the pH from the hydronium concentrations, and here's the pHs. So I have a couple questions for you. Based on the data in the table, which is a stronger acid, hydrofluoric acid or acetic acid? So when you look at that, I hope you can say that hydrofluoric acid is stronger than acetic acid. And the reason you should know, a couple reasons. You can just look at the percent ionization, and hydrofluoric acid donates more, a higher percent of its hydrogen ions. So it dissociates more, so it's going to give you more hydronium, so therefore a stronger acid. A quick way of seeing it is looking at the pH. The lower the pH, the stronger the acid, and hydrofluoric acid has a lower pH. So the answer to that first question is hydrofluoric acid is stronger than acetic acid. The second question, why does the 0.1 molar hydrochloric solution have a lower pH than the 0.1 molar acetic solution? So the concentration of these acids are the same. So a lot of students think that the pH should be the same. But remember, the hydrogen ion concentration and the pH are inversely related. So if the hydrochloric acid, even though they're both 0.1 molar, it's going to dissociate 100%. So it's going to give you a lot more hydrogen ions. So therefore the pH is going to be lower. The more hydrogen ions, the lower the pH, an inverse relationship. For acid solutions made in equal concentration, so that's just what we were talking about. In our last example, it was 0.1 molar. So if you have equal concentrations of different acids, the stronger acid, another way I could say that is the stronger electrolyte, is going to produce more hydrogen ions in solution and then give you a lower pH value. So fill in the blanks here to see how well you're understanding this. So weak acids produce fewer hydrogen ions and give solutions that are, and fill in the blank with higher or lower while I grab my pen. Okay, so if it's a weak acid, you're not going to have as many hydrogen ions, therefore you are going to have a higher pH. I'm trying to stress the point that if you have few hydrogen, you're going to have a big pH. A big hydrogen ion, low pH, inversely related. Strong bases are formed from your metals in groups 1A and 2A, forming hydroxides of those metals, including lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxides. Since they're strong bases, they're strong electrolytes, so we're going to expect 100% dissociation. And that's what happens. I'm showing that the potassium hydroxide is going to 100% break into the potassium ion and the hydroxide ion. Do you remember what the AQ stands for? AQ means that this is an aqueous solution. So I'm not showing it here, but what it means is that solid potassium hydroxide crystals are put into water, and then the water molecules hydrate each of those ions. Weak acids are almost all the other, weak bases are almost all the other bases that you encounter besides those metal hydroxides. They're going to dissociate only slightly in water, forming only a few ions. An example of that is ammonia. When you put ammonia in water, only a small percentage of it turns into ions. So I want you to memorize that ammonia is a weak base. I also want you to know that acetic acid is a weak acid. So those are the two weak acid and bases I want you to memorize. So know that hydrochloric acid is a strong acid, acetic acid is weak, and know that ammonia is a weak base. Okay, buffer solutions. Buffer solutions resist changes in pH when an acid or a base is added to them. They don't always hold the pH exactly constant, but they're going to resist a change to pH. They're going to try hard not to let the pH change. So here's an example of this. I have a beaker filled with water, and I put a pH probe in there, and it's telling me that it's neutral. So I have some pure water here with a pH of 7. If I add an acid, so say I put a couple drops of acid into this beaker, the pH is going to drop down, in this particular example, down to 4. So it changed 3 pH units. It went from 7 to 4 with a couple drops of acid. If I took the same beaker, so I started off with some fresh water. I'm going to get out of this pen mode and back to my arrow because it cooperates better. If I add a couple drops of base into water, the pH is going to increase. And it increases quite a bit because I don't have a buffer in this water. It's just pure water. However, if I make a buffer solution, so I start off with a buffer solution and the pH probe is telling me it's a pH of 7. Now, all buffers do not have to be a pH of 7, okay? You might want, for example, a buffer that's going to hold your pH constant at 2. And you can look up a book and see what kind of acids and bases you're going to make that buffer out of that'll hold you as close as constant as 2 as possible. In this particular example, the buffer just happens to be at a pH of 7. And if they add the same amount of hydrogen, it looks like the pH went down to 6.9. So without the buffer, it went down 3 pH units. With the buffer, it only went down 1/10 of a pH. So it did a good job of resisting a change to pH. If I put base in, so say I put the same amount of base in, the pH went from 7 to 7.1. So once again, just 1/10 of a pH unit. So buffers resist change to pH. And there it is. Buffers resist a change in pH when you add an acid or a base. Buffers in the body are going to absorb any hydronium or hydroxide that we get from food or any cellular processes in order to try to maintain a pH. Different parts of our body have different pH values that need to be held fairly constant. So we have a lot of different buffer systems in our body. For example, blood has a pH of 7.4, so we're going to have a buffer system in the blood trying to maintain that pH. So buffers are important in proper functioning of cells and in blood. So here's what I was telling you. Blood, the pH is 7.4. So a change in the pH of your blood is going to affect the uptake of oxygen in cellular processes. So it's very important. Our buffers in our body have to be really working well because for a lot of our proteins and enzymes and things to function properly, they have to be at a particular pH. So how do we make a buffer? To have a buffer solution, the solution must contain a weak acid and a source of its conjugate base. This throws people off when I say a source of its conjugate base. I'm going to get my pen back. Okay, so 2 things we need. We need to start off with a weak acid. It can't be any acid, it has to be a weak acid. And then the second criteria is the other component you're going to add. So you're always going to put 2 things together when you make a buffer. A weak acid, and then the other component has to contain the conjugate base. Now remember that the conjugate base of an acid is always a charged particle. It's always an anion because you have removed a hydrogen ion. So in nature, you can't just go buy a bottle of an anion. Nature produces compounds that are neutral. The amount of positive charge equals the negative charge. So you're going to go into your stock room, your chemical room, you're going to get a weak acid, and then you're going to try to find a solution that contains the anion, the conjugate base of that acid. So we need a weak acid and then a source of its conjugate base. So let's look at some of these. Gotta find my arrow. Here we go. Acetic acid, you guys are going to memorize as weak. So that meets criteria 1. I'm going to put a 1 out here. Just I want to really emphasize we have 2 criteria we need to meet. So it meets criteria 1. It's a weak acid. Does my other component contain the acetate ion? Does it contain the conjugate base of acetic acid? Well, let's draw the conjugate base. The conjugate base of acetic acid is going to look just like acetic acid, except it's going to not have that hydrogen ion, and it's going to have a negative charge. So does my second compound contain CH3COO? And it does. It doesn't show this minus sign because the sodium is coming along with its plus sign, so it's going to balance out the charge. So this guy right here makes a very good buffer. The second guy, carbonic acid, you wouldn't necessarily know it's a weak acid, but it is weak. So that meets criteria 1. I forgot to say this guy met criteria 2. The second criteria is, does the other compound contain the conjugate base of carbonic acid? Well, if this is carbonic acid, C2CO3, the conjugate base is going to look exactly like it, except it's going to have 1 hydrogen less. So it's going to be HCO3, and it's going to have a minus sign. So this is the bicarbonate ion. Does my second compound contain the bicarbonate ion? It sure does. There it is right there. So this meets criteria 2. So these are all examples of good buffer solutions, weak acid and a source of its conjugate base. You can also make a buffer by doing the opposite, taking a weak base. So ammonia is a weak base, and then finding a source of its conjugate acid. So let's go over that. If this is the base and I want you to draw the conjugate acid, you're going to say, okay, bases accept hydrogen ions. So when this ammonia accepts a hydrogen ion, I'm now going to have 4 hydrogens instead of 3, and that hydrogen ion came with a positive charge. So here's the ammonium polyatomic ion. Does my other compound here contain ammonium? And the answer is yes. So it meets 2 criteria, a weak base and a source of its conjugate acid. So a learning check, which of the following combinations make a good buffer? If we look at A, and ask ourselves, does it meet criteria 1? Does it have a weak acid? Well, no. You're going to memorize hydrochloric acid is strong. So we're going to throw out A right off the bat because it's not a weak acid, it's a strong acid. If we look at B, it has carbonic acid, and I'd have to let you somehow know that this is a weak acid. So it meets criteria 1. It's a weak acid. Now let's go look at the second compound and see if it is a compound that contains the conjugate base of this acid. Well, acetic acid, the conjugate base, is going to be the bicarbonate ion. So does this compound contain the carbonate ion? Yes. So this meets criteria 2. So B would make a good buffer. If we look at C, I see phosphoric acid, and I'd have to let you know this is a weak acid, so it meets criteria 1. Does my second compound contain, is it a source of the conjugate base? Well, if this is phosphoric acid, H3PO4, its conjugate base is going to be 1 hydrogen less than that. So it'll be H2PO4 with a minus sign. Does my second compound contain H2PO4? No. So this does not meet criteria 2. So C is not going to make a good buffer. Looking at D, I have acetic acid, and I don't have to tell you it's weak because you're going to memorize it's weak. And here is the source of its conjugate base. So D would also make a good buffer. So B and C would make a good buffer. There is something called the buffer action. So basically how a buffer is going to work. So how do buffer solutions resist a change to pH? The pH of a solution is going to change. 2 different scenarios will change the pH. Either adding an acid, which increases your hydrogen ion, or adding a base, which is going to increase your hydroxide ion. So let's look at this particular example. I have a buffer, and it's a good buffer because acetic acid is a weak acid. And here is the acetate ion, which is its conjugate base. They're not showing us the metal that had balanced off the charge, but that's pretty irrelevant to the buffer. What we really want in the buffer solution is the acid and its conjugate base. So if I were to add, so we're starting off here with my buffer, and I'm going to add acid to it. Now, what is the acid going to react with? Is the acid going to react with the acetic acid, or is the acid going to react with its conjugate base? We haven't mentioned it before, but acids don't react with acids. Okay, but we have talked about how acids react with bases. So if I add an acid to a buffer, it is going to react with the conjugate base, and it's going to donate a hydrogen ion, like all acids do. The acetate ion will accept that hydrogen. Well, what does the acetate ion become when it accepts a hydrogen? It just makes more acetic acid. So what happens is my acetic acid concentration increases. My acetate ion is going to decrease because it combined with the H+. But in doing that, okay, so I've changed the ratio of my acid and my conjugate base, but I have used up the hydrogen ion. So the pH is not going to change because there's no hydrogen ions floating around because it was neutralized by the acetate ion, that conjugate base. If we go the opposite direction, if I add a base to a buffer solution, the base is going to produce this hydroxide in water, and what the hydroxide is going to do is it is going to react with the acid because bases and acids neutralize each other. So what tends to happen in this scenario is the acid is going to give up its H to the hydroxide and turn into water. And then what is left is that acetic acid then turns into the acetate ion. So what happens in this scenario is I'm going to have less of my weak acid and I'm going to have more of its conjugate base. So once again, the ratios in my buffer changed, but I don't have any hydroxide floating around. So my pH is not going to change. So that's how a buffer resists a change to pH. If you add an acid, there's a base in the buffer that's going to quickly come up and neutralize it. If I add a base, then there's an acid component that'll neutralize it. So buffer action occurs as the weak acid in a buffer neutralizes any added base, or the conjugate base in the buffer will neutralize any acid. The pH of the solution is maintained because the hydrogen or the hydroxide concentrations don't change. The amount of an acid or a base that can be added to a volume of a buffer solution without the pH changing is what we call the buffer capacity. So every buffer has a certain buffer capacity, and you can break that buffer capacity. You can add so much acid to a buffer that at some point it no longer is going to function as a buffer anymore. So in the blood, it is critical that the buffer capacity of the blood not be exceeded, because it's important that the pH of blood be maintained between 7.35 and 7.45. So you don't have very much leeway before things start messing up in the blood. So you need a very good buffer that can keep it. It can only change 0.005 of a pH unit each way. If the pH drops below 7.35, a condition called acidosis develops, which may lead to coma or death due to the denaturization of protein catalysts, which are the enzymes. So you don't want your enzymes to break down. If the pH raises above 7.35 or 45, a condition called alkalosis develops, which may also lead to coma or death. So you can see how important it is that your buffer systems are working well in the body. Some of the buffer systems in the blood would be using the carbonate ion and the bicarbonate ion. Those make a buffer in your body. And then there's this buffer where you have a protein in the phosphate ion that becomes a buffer. These guys normally are what keep the blood at the proper pH. In an average adult, cellular metabolism releases about 16 moles per liter of hydrogen ions. That is quite a bit. That's a surprising amount of hydrogen ion that is produced through some of your cellular metabolism. So it's going to push all these hydrogen ions into the extracellular fluid every 24 hours. Yet buffers in the blood keep it at a pH of 7.4. So I don't know if that's as amazing to you as it is to me, but you've got to have a really good buffer that can neutralize that many hydrogen ions in 24